Section 3.5 deals with transformations of parent functions. Now, hopefully you already have the notes about parent functions. That isn't given in our textbook, but it's kind of expected knowledge. So make sure that you have looked at that and you know how to graph parabolas, square roots, cube roots, cubics, absolute values, and reciprocal functions. And we're going to talk about transformations. So remember that f of x is going to mean any parent function. So like if I say y equals f of x plus 4, replace f of x with any of the parent functions like square root, x squared, any of those. So I'm just going to be working each time on this page with the square root of x so you can see the difference between each of the graphs and what those transformations do. Down at the bottom of the page, I want you to add this in here. So I'm talking about any function, y equals any parent function, and I'm going to show you where the transformations would be written. So like, for example, here I have a 3 inside versus having 9/5 out in front of the f of x. So that's going to make a difference in what that transformation does. Like here I have a plus 4 in with the x and a plus 4 outside of the function. So like that would be the difference. X plus 4 inside the parent function square root and then after the parent function. Okay, so let's get those going. If you have a number added or subtracted after your parent function, so like f of x plus 4, like that one, which would look like this, square root of x plus 4. If it is after the function or not inside with the x, that is going to shift your graph up or down on the y-axis. So this, if it's added, it's going to be a shift up by however many units. If it's subtracted, it's going to be a shift down by however many units. And that is going to affect the place that we start graphing our graph. So shifts are going to affect where we start. Stretches, compressions, and reflections are going to affect our pattern. If we have a number added or subtracted inside with the x, that's going to shift our graph left and right. Now, the weird thing about any numbers that are inside these parentheses, inside the parent function, like inside the square root, like all of these that are inside, they do kind of the opposite of what you would think they do. So instead of this adding that would shift it right, it's going to shift it left. So this shifts left, and subtracting shifts right. When we have a number multiplied out in front like that, that is going to give us a vertical stretch or compression. So it's going to be a stretch if that number is bigger than 1. And it is going to be a compression if that number is bigger than 0 but smaller than 1. So what happens if that number is negative? Because we've said it's going to be either between 0 and 1 or bigger than 1. If that number is negative, then it's going to be a reflection over the x-axis. So it kind of flips that graph upside down across the x-axis there. The last one we have to talk about here before we get started on our examples is if we have a number multiplied by the x inside the parent function. And that is going to give us a horizontal stretch or compression. But remember that anything that's inside does the opposite thing that you would think of. So this one does a stretch, horizontal stretch, if our number is between 0 and 1, and a horizontal compression if that number is bigger than 1. And again, if that number is negative, that's going to be a reflection, but this time it reflects over the y-axis. So any of our numbers that are inside that parent function, anything inside that parent function is going to be a change going like this way, left and right. So it either shifts left, shifts right, or it stretches horizontally or compresses horizontally, or it reflects over the y-axis. So everything that's in there is related this direction. Anything that's outside of the parent function shifts up or down, stretches vertically or compresses vertically, or reflects over the x-axis. So things that are outside the parent function, not inside with the x, are going to be uppy downy changes. Things that are inside are going to be lefty righty changes. Okay, let's get some examples. First of all, we need to remember what that square root function normally does. So I just want to remind you that if we have that parent function y equals square root of x, that's the one I call an eyebrow. It will normally start at 0, 0. It's not, I don't know that you really call it a vertex like you do with a parabola, but that's just our starting point. We start at 0, 0, and then we're going to, from that point, move to the right 1, up 1, and then go back to that start point, move to the right 4 and up 2, and then back to the start point again, move to the right 9 and up 3. So that's our parent function. All of our other transformations are going to start with that information. So here we've got f of x plus 4. So my example is square root of x plus 4. That adding 4 is outside of the parent function. So that is going to give us a shift up 4. And that shift up 4 is going to affect our starting point. So when we shift up 4, that's going to add 4 to the y coordinate. So our start point is now going to be 0, 4, but it's not going to affect our pattern. So we would still go over 1, up 1, over 4, up 2, over 9, up 3. So we go to 0, 4. From 0, 4, we go over 1, up 1, then go back to 0, 4, over 4, up 2, go back to 0, 4, go over 9, and up 3. And that's going to be what that new eyebrow graph looks like. Compared to this one, in this one, the plus 4 is inside the parenthesis with the square root of x, and so that is going to be a shift left or right. Inside the parentheses goes the opposite direction that you would think. This does a shift left of 4, so that also affects our starting point. So instead of starting at 0, 0, we shift left 4, 1, 2, 3, 4, and we're going to start from negative 4, 0. Now, another way to think of that is to take what's inside that parenthesis, x plus 4, and set it equal to 0, subtract that 4 over, and that's going to tell us that x equals 4 would be our new starting point. The pattern is not going to be affected, so I'm still following the same pattern to get the rest of my ordered pairs. So I go over 1, up 1, back to the start, over 4, up 2, back to the start, over 9, up 3. So you notice that these graphs have the same shape, but they just started in a different spot. These two are going to be similar transformations. They are outside of the parent function. So we have 9/5 times the square root of x and 5/9 times the square root of x. Those are these little guys out front, a number out front. So it's going to be a vertical stretch if that number is bigger than 1, and a vertical compression if the number is between 0 and 1. That's because we're multiplying our height by the number out front. So I'm multiplying my height by 9/5 makes me taller. Multiplying my height by 5/9 makes me shorter. So this guy is a vertical stretch because the value is over 1. And this one is going to be a vertical compression. Neither one of those is going to affect our starting value. So we're still going to start both of these at 0, 0. That's going to be our start point. But what we have to do when we are changing, like we're applying a vertical stretch or compression, is we take our pattern. We're still going to go over 1. I'm just going to write out the normal pattern. Over 4, up 2, over 9, up 3. But what I need to do is multiply my heights or my ups by that stretch or compression. So I do times 9/5 times 9/5 times 9/5. So instead of going over 1 up 9/5, I'm going to go over 1 up, over 1 up 1, I'm going over 1 up 9/5, which is close to 2. Instead of going over 4 up 2, I'm going to go over 4 up 18/5, which is getting close to 4. And then over 9 up 27/5, which is bigger than 5. So I'll still start from 0, 0, but I'm going to go over 1 up almost 2. And then I go back to the start, go over 4 and up almost 4. And then go back to the start point. I wish I would have labeled these. Over 9, up bigger than 5. So when you compare this shape to the shapes that we had that didn't have stretches, it should look like we grabbed the graph and stretched it this direction. It just got like taller, but the x values didn't change. We just stretched the y values. And then on this one, we're going to follow the exact same steps. We'll take our regular pattern, but we multiply our ups by that number out front. So 5/9, 5/9, 5/9. So our over 1 will go up 5/9, which is a little bit bigger than a half. So over 1 up a half. And then over 4, whoops, I got my arrow going wrong. Over 4 up 10/9, which is just a little bigger than 1. And then over 9 up 15/9, which is like close to about, well, that simplifies to 5/3. Close to 2, but not quite 2. So over 9 up close to 2. So compared to our normal shape of graph, this one is squished. So like the x coordinates didn't change. We just vertically compressed the y coordinates. So it makes it look like short and squatty. Okay, comparing that to when our number is inside with the x's instead of outside, these are horizontal stretches and compressions. If that number inside is between 0 and 1, that's a horizontal stretch. So let's get that going. On a horizontal stretch, what we're going to do is divide by that number. We're going to divide our x values or our overs. It's like when we go over 1, up 1, over 4, up 2. We're going to divide our overs by that number. Another way to think of that is to multiply by the reciprocal. So when we have a horizontal stretch or compression, we're going to do that same strategy. We're going to multiply the overs by the reciprocal of that number. Now that's not going to affect our starting value. So our starting point is still going to be 0, 0. But this time, when I go over 1, over 4, over 9, I'm going to multiply those overs by the reciprocal of 1/3. So that turns my 1/3, flips it upside down, makes it a 3. So I'm doing times 3 on each of these. So I'm going to go over 3 and still go up 1. Go over 12 and still go up 2. Go over 27 and still go up 3. Now that one's not going to fit on our graph, but we'll get the other ones on there. So I still start at 0, 0, and then I go over 12. Oh, sorry, I have to start with 3. Over 3, up 1. Then go back to the start, go over 12, and then up 2. And then my next one would be over 27 and up 3. So let's graph that. So you see what we've done is we've taken a horizontal stretch. So like grabbing the graph this way, keeping the y values the same, but stretching the x values out that direction. Notice that doing a horizontal stretch resembles doing a vertical compression. So physically they look the same, but we're doing different things to the ordered pairs. On a vertical compression, I'm squishing the height of each of the x values. On a horizontal stretch, I'm stretching out. Did I say the height? Those are the y values. So I keep the x values the same. I compress the y values. On this one, I keep the y values the same and I stretch the x values. And you're going to see that a vertical stretch does the same, only the reverse direction. So vertical stretch, I keep the x's the same and I stretch out the y's. Horizontal compression, I keep the y's the same, but I compress the x's. So they end up looking similar. When I do that, the graphs will resemble each other. So same thing, same process here. When I have a horizontal compression, I'm going to multiply the overs by the reciprocal. So I keep my same over 1, over 4, over 9. The ups are not going to change, but I'm going to multiply my overs by the reciprocal of 3, which will be 1/3. So I'm going to go over 1/3 up 1, over 4/3 up 2, and over 3 up 3. So I still start from the same place. That didn't change with the compression. 0, 0. I go over 1 up 1, over 4 up, oh, excuse me. Oh, I messed that up. Over 1/3 up 1, over 4/3 up 2, and over 3 up 3. So this graph gets real tall real fast. So here we've got a vertical stretch and a horizontal compression looking similar to each other. Okay, on to our reflections. So if we have a number, remember, if we have something outside the parent function, that's changing our graph vertically. If we have a number inside, that's changing our graph horizontally. So here we've got a reflection over the x-axis because we're going this way. And then this one will be a reflect over the y-axis. So when we reflect over the x-axis, one way to look at that is to multiply all of our y values by -1. Another way to look at it is to say that it's going to turn your ups into downs and vice versa. If you like when you get on the reciprocal function, you have downs, so it turns your downs into ups, turns your ups into downs. It just flips everything upside down. When we're reflecting over the y-axis, it's going to turn your over to the rights into over to the lefts, and vice versa. If you have any over to the left, it's going to turn those into over to the right. So you're just flipping the direction left and right. It's not going to change our start point, so we're going to still have 0, 0. But now when I go over 1, I'm going to go down 1. And when I go over 4, down 2. Over 9, down 3. So I start from 0, 0, go over 1, down 1, over 4, down 2, and over 9, down 3. So it just looks like an upside down eyebrow. And then when I reflect over the y-axis, I still start at 0, 0, but instead of going to the right 1, I go left 1 and still up 1, then left 4, up 2, and left 9, up 3. So starting at 0, 0, left 1, up 1, left 4, up 2, left 9, up 3. So that just looks like the eyebrow on the other side of the face. Okay. That page took a long time. Let's practice doing some of these transformations and like writing them and then graphing them. So here we've got an absolute value function that is shifted 4 units down and 5 units left that has a vertical compression of 1/2. So I'm going to keep these kind of here so you can reference them as we're going. So an absolute value function is y equals absolute value of x. That's the one that looks like a V. It has a vertex at 0, 0. And then it is going to go over 1, up 1, over 2, up 2, over 3, up 3. And then it also goes the other direction to make that V. So it goes left 1, up 1, left 2, up 2, left 3, up 3. So we need to have that graph, but we need it to be shifted 4 units down. And then also 5 units left. And have a vertical compression of 1/2. So we're going to take our equation, we're going to make it y equals. We need absolute value of x, but out in front, we need a 1/2. Shifting left is going to go inside with the x. So absolute value of x, and when it's a shift left, it's add, so +5. And then we also have 4 units down, which goes at the end, and shifting down is a subtraction. So all of those transformations are going to affect either the place we start the graph or the pattern that we use to grow it. Any of our shifts are going to affect our starting point. So instead of the vertex being at 0, 0, we need to shift it down 4 and left 5. So shifting left 5, 1, 2, 3, 4, 5, puts us at -5, and down 4 puts us at the ordered pair -5, -4. So -5 from shifting left, -4 from shifting down. Let's see. So I'm going to put my start point, 4, 5, right there. And then the vertical compression is going to change my ups. So I'm going to multiply all of my ups by that half. So over 1 up, instead of 1, it's going to be 1 times a half, which makes 1/2. Instead of going over 2 up 2, it's going to go over 2 up 1 and over 3 up 3/2. And so then we have to just remember to put those mirror points over there. So we go over 1 up 1/2 and put the other dot on the other side, over 2 up 1 and put the dot, over 3 up 1.5 and put the dot over there. And then that makes straight lines connecting those. And we don't just want to draw that as a short line, like you want to extend those lines and make them go forever, because that's what those graphs do. Okay, number 2. That's a square root function. We just did a whole bunch of those on the other page. So I'm sure we remember that they start at 0, 0, and then go over 1, up 1, over 4, up 2, over 9, up 3. But we need to shift it 8 units left. 8 units left. 2 units down. Vertical stretch of 2. So that vertical stretch, remember, goes out in front. So 2 times square root. Shifting left goes inside with the x. When it's left, it's plus that number. And then shifting down goes after. And when it's a downshift, it's subtract 4 or subtract 2. So I'm going to start by shifting 8 units left, 2 units down. So my start point, instead of being 0, 0, is now going to be 8 units left. So -8, 2 units down, -2. And then my pattern, I have a vertical stretch. So I'm going to go over 1. The ups are going to change. So I multiply each of the ups by 2. So over 1 up 2, over 4 up 4, over 9 up 6. -8, -2. Over 1 up 2, over 4 up 4, over 9 up 6. And then one of the things that we might want to consider doing is always going back and writing our domain and range. So on this graph over here, absolute value, if we scan left to right, the domain would be all real numbers, as it is for the absolute value family. And the range, this one starts at -4 on our y values and then goes to infinity. The square root graph, domain, as I go left to right, the first x value that I encounter is -8. So -8 to infinity. And then the range, the first y value I encounter is -2. And it keeps going up. You'll notice that your domain and range values are going to be closely tied to your starting point in both of those, although the domain for this one's all real numbers, but the range is related to that start point. A reciprocal function. Reciprocal functions are the ones that have like a black hole at 0, 0. So that's like, it's not a vertex. It's not really a start point. It's like where we get the vertical and horizontal asymptotes. So that's normally at 0, 0. And then we have vertical and horizontal asymptotes coming out of it. So it's not like, that's not really a point that's on the graph. What we do after that is we're going to move from that black hole. We're going to move over one, up one. We also move over 1/2, up 2, and over 2, up 1/2. And then we go the same thing, but over in the other direction. So we go left 1, down 1, left 1/2, down 2, and left 2, down 1/2. So it's got like a swoopty here and a swoopty there. And the equation for that is y equals 1 over x. Okay, so on this one, we're going to shift 4 units left and 5 units down and have a vertical stretch of 3. So we'll go y equals 1 over x, 1 over x. But then I'm shifting 4 left, so plus 4 in with the x. I'm shifting 5 down, so minus 5 not with the x, and a stretch of 3, so 3 times. So that's one way to write it, but we could also write it y equals, we could do the 3 over 1 times that fraction and end up with our 3 in the numerator, and then x plus 4 minus 5. So you can see them both ways. Okay, let's graphy graph. So I'm not going to be starting my black hole at 0, 0. That is going to be shifted left and down. So my black hole is going to start from -4, -5. And that's where I'm going to draw my asymptotes, -4, -5. So I go to -4, -5. I usually do put that black hole right there, and then I draw these asymptotes. The asymptotes are like, my graph isn't going to touch or cross them on this kind of graph, and they give me a good guideline about where I should be drawing the arms of it, the branches. And then the pattern, I have a stretch of 3, so I'm going to go over 1/2 and then up. I have to stretch that out times 3, so up 6. I go over 1, and then I'm going to go up 3. And then I also go over 2, and I'm going to go up 3/2. Okay. And then I remember to do the mirror points like catty corner. So starting from that black hole, go over 1/2 and then up 6 to here. Go back to the black hole, over 1, up 3. Go back again, over 2, up 3/2. So I need to fit my graph in this little corner, knowing that the ends of the graph are going to run along that asymptote. I want to make it curve and then head along both kind of in the corner. And then do the same thing on the left side. So I go left 1/2, down 6. Go back to the start, left 1, down 3. Go back to the start, left 2, down 1.5. And again, fit my graph in that corner. This graph will have symmetry, like rotational symmetry, about its black hole. So if I rotate the whole graph, 180 degrees, holding that black hole still, it should look the same upside down as it does right side up. Okay, this graph. What we would do on this is it's asking us to apply these transformations to that parent function. So we want to analyze what we got going on. That's a vertical stretch. And then we have a shift right and a shift down. So I just take the parent function they gave me, which was y equals x cubed, and I apply a stretch out front, a shift right. The cubed is what makes it that family, and then down 5. Okay. Y equals x cubed normally. Sorry. I have a text message apparently. We start at 0, 0, and then we go right 1, up 1, right 2, up 8. We don't normally have room for right 3, up 27. And then we go left 1, down 1, left 2, down 8, left 3, down 27. That's the one that looks like, it kind of looks like a parabola that got twisted in the middle. So I am going to start, instead of starting at 0, 0, I am going to start at moving right 3 and down 5. So that will be 3, negative 5. Will be my new start point. So 3, negative 5. And then I'm going to stretch by 2. So all of my ups will be double. And all of my downs will be double. So I'll go right 1, up 2. Right 2, up 8. Left 1, down 2. Left 2, down 8. Okay. Then when you graph it, you kind of want to think about it as though it's being a parabola into the start point, and then an upside down parabola out of the start point. So that will be that graph. All right. So the final exam from Neosho County includes, I should probably not say that. Sometimes questions can be asked for you to do these transformations in order and then write the equation for what results. So we're just going to run through one of these. It's asking you to start with y equals square root of x. So we know what that one looks like. Starts at 0, 0, over 1, up 1, over 4, up 2, over 9, up 3. So make sure you get that graphed, fairly accurately. So that's going to be our first graph. Start with y equals square root of x. Okay. Then we are going to shift down 4. So down 4, I'm just going to take each ordered pair and count down 4, put a new ordered pair. Whoops. 1, 2, 3. Well, I can't count to 4. 1, 2, 3, 4. Right there. Right there. 1, 2, 3, 4. 1, 2, 3, 4. So that's my first change. Then it wants me to reflect over the x-axis. So this one's the x-axis. So I'm going to take each ordered pair and just go to the other side and draw it. That guy is going to go right on top of that one. It's right here. And then sketch that. So that's a reflection of that orange graph. Then it wants me to reflect what I have there over the y-axis. So that's the y-axis. So this point stays where it's at. This one goes over to that side. This one goes over to this side. And this one goes all the way to the other side. So now that's what I'm working with. And then finally, it wants me to shift left 2. So each ordered pair, go left 2, left 2, left 2, left 2. And then I'm supposed to write the equation for the resulting graph. So basically what I want to do is look at the purple graph and say, how does it compare to my parent graph? So remember that my parent function normally starts at 0, 0, and then goes over 1, up 1, over 4, up 2, over 9, up 3. So compared to that graph, my purple graph starts at -2, 4. And then it goes left 1, down 1. And then left 4, down 2. And then left 9, down 3. So what are those transformations? Well, the transformations from the original shifted left 2, and up 4. Remember that this guy, changing our lefts and rights, if you go back to our reflections where we talked about those, changing our lefts into rights reflected over the y-axis. And changing our ups to downs reflected over the x-axis. So we're going to take our original parent function, y equals square root of x, and we have to shift it left 2, so that means +2 inside, up 4, +4, and then reflect over the x-axis and reflect over the y-axis. So negative, negative. And that would be our ending graph. Okay, one last task we need to do, and that is completing the square so that we can graph parabolas using transformations. So I'm going to color code these steps. I know that's a shocker, but here we go. First of all, I'm going to change this to y equals x squared minus 6x, like that. We're going to do 2 examples here. The first thing we're going to do is move all of the x terms to one side and the rest of the terms to the other side. Now that's already done in our problem here, so we don't have to do that in this problem. Then the next thing we're going to do is divide both sides. I may want move in there. First move, then divide both sides by the coefficient on the x squared. Now the coefficient here is a 1, so again, I don't have to worry about that one. Okay, then the next thing I'm going to do is b divided by 2 squared. So I figure out b divided by 2 squared, and I add to both sides. That's my next step, add to both sides. So kind of off to the side, I think about b divided by 2. So that's -6 divided by 2, which is -3. I'm going to square that, and 9 is the number I'm going to add to both sides. So I take my left side and I add 9. I take my right side and I also add 9. Then my next step is going to be factoring. When I factor, I just use the number inside the parentheses. Like I literally just drop that number into a parenthesis that says x plus that number squared. If it's negative, it'll be x minus that number squared. So when I factor this, I'm going to take this number here, -3. That's what I'm factoring with. So I'm going to have x minus 3 squared. That's the only thing that's going to be on the right side over here. On the other side, I still have y plus 9. At that point, I make a U-turn. So then I go in reverse order. So I just factored. Now I'm going to reverse and subtract that number from both sides. So that's that 9. I'm going to subtract 9, subtract 9. So now I have y equals x minus 3 squared minus 9. And then the next thing I would undo is dividing that number from both sides. So I would multiply both sides by that x squared coefficient. But remember, on this problem, that coefficient was 1, so we don't need to worry about that. And then if there's anything else we need to move, remember how we had to move some of the x terms to one side and the rest to the other side? Then we move back. So we have y equals by itself. So this one is already done, this problem, and then we can list the transformations and we would be able to graph it. So on this one, the transformations, the only thing we have is a shift right 3 and a shift down 9. So we would graph that by putting the vertex at its normal, from its normal spot of 0, 0. We would make it 3, negative 9. And then nothing changed the pattern, so we go over 1, up 1, over 2, up 4, over 3, up 9. Okay, let's try this example. It's a little bit more complicated, so that's good. We're going to follow those same steps. So the first thing is to move all the terms that have x's, keep them on one side, and move the rest to the other side. So I'm going to remember this is a y. So I will add that 13 onto that side. So I have y plus 13 equals negative 2x squared minus 12x. Next step was to divide both sides by the coefficient of the x squared. Now, when we do that, I want you to put the entire left side, just keep it all over negative 2. But on this side, I want you to divide each term by negative 2. So then we're going to end up with y plus 13 all over negative 2 equals x squared plus 6x. Next up, do the b squared divided by 2, add that to both sides. So now we've got b is 6, so I'm going to do b divided by 2 squared, so 3 squared. 9 is what I'm adding to both sides, so I'm going to go plus 9 plus 9. And then my next step is to factor, but I just use that b over 2 number. So I'm factoring with 3. So that's going to make my right side be x, it's positive 3, so x plus 3 squared equals, and the left side just stays the same. And after the factoring step is where I U-turn. So then I start undoing things. So the first thing that I'm going to undo is the adding 9. Like I just added 9 to both sides before I factored, and now I'm going to U-turn and start undoing everything. So I subtract 9 from both sides, which is going to give me y plus 13 divided by negative 2 equals x plus 3 squared minus 9. Then the thing I did prior to that was dividing both sides by negative 2. So I'm going to undo that by multiplying both sides by -2. Now, when you do multiply by -2, that's going to cancel out that -2. We have to multiply the parenthesis by -2 and that constant term by -2. So on the left side now I have y plus 13. On the right side I have -2 times x plus 3 squared. And then that's going to be plus 18. Okay. And then right before I had divided by -2, I added 13. So the next thing I need to do is subtract the 13. And I end up with y equals -2 times x plus 3 squared plus 5. And now I have my parabola in vertex form, so I can graph using transformations. This is reflect over the x-axis. We have a vertical stretch of 2, a shift left 3, and a shift up 5. So those shifts are going to change where the vertex is. So instead of 0, 0, it will be at -3, 5, because we went left and up. Reflection over the x-axis is going to change all of our ups into downs and downs into ups. So we're still going over 1, and then instead of going up, we're going down. Vertical stretch of 2, so over 1, up 1 becomes over 1, down 2. Over 2, up 4 becomes over 2, down 8. Over 3, up 9 becomes over 3, down 18. And remember that that's a parabola, so we have the mirror points. So you got to make it into that shape when you draw it.